Thank you. Hi, everyone. My name is Ran Hu. I am with Huawei's Big Data Platform team. And last year, I worked with Mr. Fang Cao, Min Chu, and Yizhen Liu. 4 of us did proof of concept for a big data project. We developed our solution on top of Apache Spark SQL. And at the beginning of our project, we quickly noticed that Spark SQL Optimizer did not collect the detailed column statistics. So in order to improve the quality of the query plan, we decided to enhance Spark SQL Optimizer with some reliable statistics. So in this talk, I will share our experience with you. So this is an overview of today's agenda. We will quickly talk about Spark SQL's rule-based optimizer, and then what kind of statistic information we collected, and then how we added some course-based rules, and also some future work. I think we have seen this diagram, multiple times. For most of our work, we did that in the logical optimization area. Okay. We found out that most of Spark SQL's optimizers rules are the heuristics rules. So it does not consider the cost of each execution operator. Also, it does not consider the cost of the equivalent logical plans, okay, when you try to perform some transformation. And in the early days, the join order of the Spark SQL was decided by its position in the SQL queries. Okay, and the join type is based on some very simple system assumption. Also, such as number of shuffle partition, it is a fixed number. And our team, we have fixed several performance bugs in order to improve TBCH queries performance. And we gave a talk in this year's Spark Summit East, back in February. As for what statistic information we collected, there are 2 levels. One is a table level statistics. The other is column level statistics. And after we collect the statistics, we also look at the system configuration, such as number of CPU cores and the network bandwidth, etc. Then what is our goal? Our goal is to calculate the cost of each database operator in terms of number of output rows and also the output size in bytes. And based on this cost calculation, then we try to adjust query execution plan in order to reduce query response time. As for the table level statistics we collected, we utilize a modified Hive analyze table statement to collect statistics. For example, here we have, we analyze table, we have this statement, analyze table, line item, compute statistics. Line item is a table used in TBCH benchmark. And the table level statistics information we collected are, number of rows, number of files, or you can say it's the number of HDFS data blocks, and also table size in bytes. We also collect more detailed column level statistics. Okay, still we utilize the analyze statement. Okay, say for example here we analyze table line item compute statistics for columns L order key, L part key, L supply key, etc. Usually you do not need to collect statistics for every column of a table. You only need to collect statistics for those columns specified in the where clause. You have some filtering condition, or the column is utilized in the group by clause, or the column is utilized as a join column. As for the detailed information we collect for each column, we collect a minimum value, maximum value, number of distinct value and the number of null values, and also columns maximum length and the column average length. For some scalar data type, such as integer, long, or short, okay, the maximum length is same as average length. However, for the string data type, they can be very different. Also, based on the information, we can compute whether or not a column is unique. And with a Hive analysis statement, what kind of format do we save this statistic information? We provided two kinds of histogram, equal width and equal depth. For example, in this diagram, okay, we have the equal depth. Equal depth means that the width of the column interval is fixed. Say, for example, we have 600 distinct values. Then for the equal width histogram, then suppose the interval is from 0 to 600. Then for the first interval is from 0 to 100. Second interval is from 101 to 200, etc. That is equal width. However, in real world, very often we have the skewed data distribution. We have found out that it would be better to utilize equal depth histogram. Basically, is the width of the column interval, is not fixed. It can vary, okay, depending on how sparse and or how dense each interval is. And the maximum number of buckets we utilize is 256. So if the number of distinct values is less than or equal to 256, we use equal width. And the number of distinct values is greater than 256, then we use equal depth. Equal depth means that it's a height balance, okay? And we use Hive Metastore API to fetch the information. In addition to the one-dimensional histogram, we also supported two-dimensional histogram. Two-dimensional histogram is basically we collect statistics for a combination of two columns. Usually, when you suspect that two columns are correlated, then you may want to create this two-dimensional histogram. Because there are two columns, C1 and C2. One is a major column, one is a minor column. For C1, suppose we still have 256 buckets, for the total number of buckets. Then for C1, we can only have like 16, okay? For C2, we also have 16. 16 times 16, that's 256. Okay. The lesson we learned is actually, users do not use two-dimensional histogram often. The main reason is most of the time they do not know which two columns are correlated. Another thing, another difficulty we face is what is the granularity level? How many buckets do we use? If we just use 256 bucket, then for the first columns, like C1, we can only have like 16 bucket. 16 bucket is kind of the granularity is kind of coarse. But if we have still maintain 256 buckets for C1, then for C2, another 256. Then we times these two numbers together. Then we need to save lots of information in the two-dimensional histogram. And so basically, and also in real world, sometimes it's more than two columns are correlated. It can be 3 columns, 4 columns, or 5 columns. We found out that the problem, the granularity problem we just mentioned, is more difficult to extend to the 3 dimensions or more. And we found out that our user they rather want us to provide some SQL hint, because SQL hint is simple and direct. Okay. So in the previous talk, we know that sparse SQL optimizer basically is a rule executor. Individual optimization technique is defined as a rule. For us, we still maintain a catalyst architecture. So we basically added some new rules to estimate the number of output rows and the output size in bytes for each execution operator, such as meta-store relation. Meta-store relation actually means a table scan, filter, project, join, sort, aggregate, etc. And the cost of each execution node is a function depending on the number of rows and also the output size in bytes. Because in Spark SQL, there are quite a few execution operators. Here, I'm going to give you some example how we compute the number of output rows for filter and the join operator. For filter operator, okay, so basically you have some expression, okay. Usually, you have comparison, in a single expression, you have comparison operator equal, less than, etc. And then you can combine, multiple expression to form a complex or compound expression by using logical AND operator or logical OR operator. Then for ending condition, such as a column, here we have column A, this OP means is a comparison operator with data B. Okay, B is a constant. For this case, okay, then how do we compute the filtering factor? Okay, so because we collect a minimum value and the maximum value of column A, so we know its interval. If the constant B falls behind, if it is less than the column A's minimum value, then we know that the filtering factor is 0%. This means that no records qualify for this condition. But if B falls between the column A's minimum value and the maximum value, okay, like such as this case, then it depends whether or not we have histogram information. Without histogram information, we have to assume that we have even distribution between minimum value and the maximum value. Then we just compute the proration to decide its filtering factor. But if we have histogram information, then we can do some calculation. We can look at each interval one by one and then add the number of distinct values together. And then it will be divided by the overall interval. Then we can find much more precise information, okay, for the filtering in factor. If constant B is greater than the column A's maximum value, then basically, then all the records will meet this condition. Then the filtering factor is 100%. Another case will be, column A, then you have a comparison operator against column B, okay, for this case. For this case, then, there are multiple cases we need to consider. Say, for example, A and B, they do not overlap, but A's range is smaller than the B's range. Then its filtering factor is 100%. And on the opposite, entire B's range is less than A's range. Then here, we said that its filtering factor is 0%. But the most common cases is A and B overlap. For example, in TBCH, there are some queries. We want to find out those orders that the commit date is less than the receipt date. Basically, initially you commit certain date, but on that day, there are some delay, and you fail to ship, or based on commit date. For this case, as of today, we just utilize some empirical data. We set the filtering factor to 1/3, okay. But it is possible, to expand this so that you will go through, you would really do some comparison. Okay, I mean, you perform some calculation. The next thing I will briefly talk about will be the join order, how we handle the join operator. We basically consider, two-table join. Okay, for the hash join operation. Okay, hash join operation, usually we want to use a smaller relation as the build side, and you use a larger relation as a probe side. Okay, then in order to figure out, which table is smaller, we have a cost function. This cost function again, it is a function and dependent on number of rows and also the table size. Here, 0.7 and 0.3, these are the weighting factors. Okay, and we want to choose the lower cost child as the build side of the hash join operation. Another one is that in TBCH, most of the queries are the multi-way join queries. Okay, and currently Spark SQL join order is not decided by the cost of multi-way join operation. And we decided the join order based on the output rows and the output size of the intermediate table. Our strategy is, suppose you have, say, like a 5-way join. Then we look at, each join and then see which join will produce the smaller output. Then we will run that join operation first. Okay, and we notice that for TBC DS benchmark, because the database itself is a typical star schema. You have fact table in the middle and then join with other dimension table. So actually, it's very easy actually you can perform the join between the fact table with any dimension table first. Okay, the key is to find out the output size of each join and then perform those join with a smaller output first. And here, one of the author, Mr. Fang Cao, he designed an algorithm using dynamic programming. Basically, if you use dynamic programming in a technique, you can find globally optimal join order. Okay, but due to limited time, I do not have time to go into detail for this. And here, this is a query execution plan for TBCH Q3. It's a 3-table join plus aggregate. Okay, all these boxes are the execution operator, and we basically compute the number of output rows and also the output size. Okay, for each operator, and then for this box, we perform the shuffle hash join. For this one, without our statistics, the system will choose, say, build right. It will use the right child relation, as a build side. But with our statistics, okay, then we change to build left. We want to use the left side as the build side. Okay. Of course, the left side, we do not get the base table information directly. It goes through many operators. Okay. So basically, all the statistics will be derived from one stage to next stage. Next thing I want to talk about, we are able to compute to find out whether or not a column is unique. Spark SQL does not support index or primary key. Without this information, sometimes it is difficult to figure out the size of the join output. This is because in real world, most of the join operation are the primary key and the foreign key join operation. If you know one join column is unique, okay, then you can estimate the join output very precisely. Okay. Another thing is that for the group by operation, when you have a group by and then you say group by C1, C2, and C3, If you do not know, one of the column is unique or primary key, then you will set, when you try to estimate the output size of the group by operation, then you will times a number of distinct value on C1 times number of distinct value on C2, and then number of distinct value on C3. Very often, you will get a huge number, okay? And for group by, the most efficient way is to use a hash table. But when you get a large number, the system may think that you will run out of memory. So instead of using hash table, then it may switch to use some sort or operation. So definitely you can. It is beneficial, and you can improve or the query response time if you have better statistics, and then you can apply the right strategy. For us, we are able to compute to find out whether or not a column is unique. This is because we collect the number of distinct value for each column, for the column. And then we know the number of records for the table. So when you compute the ratio of the number of distinct value over the number of records in a table, if int is close to 1, then you can assume that int is unique, okay? When int is unique, say for example, like here, I use TBCH Q10, okay, Q10. In this query, you have group by, okay, group by C class key, C class key, C name, C account balance. All of this C underscore something, they are the columns belonging to customer table, okay? But actually, for this table, C class key is unique. It is the primary key. So without this unique, column uniqueness information, then if you times the number of distinct value for all of them together, then you get a huge number, okay? Huge number. But if we say that this column is primary key, then there's no need to times its number of distinct value with number of distinct value in the customer name, account balance, etc. Then you can have a much better idea on the number of the output rows for the group by operation. Say for example, see in our case it's only 82,000. It's like 2 or 3 order of magnitude smaller. Next thing is here I want to briefly mention that we also provide a SQL hint. As you know, for many database vendors, they provide a SQL hint when their query optimizer is not mature yet, okay? But that is the first situation. There is also another situation. Basically, some information just cannot be analyzed or compute directly from the statistics of the table and the column. Say, for example, like this one, TBCH Q13. Here, there's a condition, O column not like, okay? You have % sign, special, % sign, rest, request, and then % sign. Basically, here, the pattern, as for the string pattern, it can be a regular expression, okay? If the regular expression, if there's no % sign at the beginning, then this string is like beginning with something. That will be easier to find out its statistics. But when you have the regular expression like this, it's very difficult, to figure out its statistics, okay? So here, we supported a SQL hint. It's a like filter factor, or let DBA tell you how much it is. Another one is also in this query, there's a group by CCount. What is a CCount? It's a derived column from this subquery, okay? And for this one, actually, DBA can quickly figure out because if you take a quick look at this subquery is basically, find out those customers that have not make, special requests, okay? And the DBA usually can quickly find out, saying that our database is for the past 5 years. And a customer will make, how many orders, per year. Then you can quickly figure out, what this number is, okay? So here we also provide some NDV, number of distinct value, for something, for the derived columns, okay? And then here, now I want to show you that I want to do some comparison between the actual number of the output records for TBCH query. And also, when we utilize our statistic information, what estimate numbers we can provide. So you can see that for most queries, okay, our estimate number is not that far away from the actual number, except for query 3, Then you may wonder, what happened to query 3? For TBCH query 3, the reason we cannot handle it well is because this group by is L order key. This column comes from the line item table. The second one is O order key. This column comes from the order table. Because today we do not handle the correlated columns, of different tables. So for that query, we were not able to provide good estimate. Okay, then the next, I want to share with you, some performance comparison we did. For TBCH queries, okay, we use a base. The base is a Spark SQL without statistic information. And then we run on Spark SQL with our statistics information, and then we do some comparison, okay? And for both cases, they both utilize the same Spark SQL execution engine. So you can see that for some query, there's no speed up, okay? But for about, I think a little bit more than 50% of the queries, we are able to adjust the query plan, okay? Because we have some reliable statistics. And then we are able to reduce query response time. The range can be, from 2 times, and for one case, we are able to get, 6.5 times faster. The overall average for all the TBCH queries, we are able to double TBCH's query performance. Okay. Basically, we can reduce the query response time by 50%. Okay. Finally, I want to quickly mention the possible future work we may do. Today, we use full table scan operation to collect statistics. We can get correct statistics, but it is kind of slow for very large table, okay? And in the future, we may want to try some sampling in techniques, okay? That's a quick way to find out statistics. And also today we only collect statistic information for the columns and the table directly, but we do not collect statistics information for some derived column, like such as some aggregation expression, or even some UDF, user-defined functions, okay. And also, as you know, data streaming has become more and more popular, okay. So after you collect statistics and some new data keeps coming in, okay. At that time, how do we still, provide the real-time statistics for query optimizer? This is some future work we may take a look. So this is the end of my talk. So thank you for coming. If you have any question, we just run out of time. If you have question, I will be happy to answer you offline.